All right, thank you so much for coming to my talk. So this talk is called Forget This Sandbox Escape, Abusing Browsers from Code Execution. It is gone. All right. So basically what we're going to be talking about is we can take a browser exploit, and normally you would need a sandbox escape. So we're going to be trying to look at ways that we can continue to abuse the browser without actually needing to escape the sandbox in the first place. So first, a little about me. My name is Amy Burnett. I am one of the co-founders of Ret2 Systems. I do vulnerability research, specifically focusing on browsers and looking at different ways to bypass mitigations in browsers. And I run a browser exploitation training, which I've done a few times, which has been pretty cool. Also, as we mentioned previously, we ran an entry in Pwn2Own 2018 for Safari, so we would get root on Safari. So the motivation for this talk is that sandbox escapes are expensive. Sandbox escapes is usually the second part of a chain of exploits that you have for a browser. It will require a second bug in whatever you're looking at, whether it's the operating system or you're trying to exploit, let's say, a system service or something like that. So it can be a lot of extra engineering time to find that bug and then write an exploit for it. But also, there's begun to be a lot of interesting information that is stored entirely within the browser itself. For example, your browser has access to things like your bank accounts, sensitive documents, whether they're on the LAN or in the cloud, your email messaging history, and it's also where you download software. So this is a location that you put a lot of trust into the browser. I'm going to quickly just go a little bit over some browser architecture if people aren't really familiar. Browsers are broken up into a bunch of different processes. The main one is usually whatever application you opened. There'll be some helper processes like the network process and the GPU process. But the main one that we're interested in is this one called the renderer process. So now the renderer process is sort of where all the magic happens, and it deals with all the actual HTML and JavaScript on the web. So from an attacker's point of view, that will be the first place that we approach. We'll be looking at the renderer. And in most situations, an attacker will have exploited this renderer process. So they will have compromised this process using some bug. Along the way to compromising the process, they will have gotten arbitrary read-write in most cases. Arbitrary read-write is basically the idea that they can write to any memory address in the process. So from JavaScript, they can now read and write to anywhere they want within the renderer process. And we're going to look at some talks today that will be, you can pull them off with only the read-write without needing to get full code execution. But often attackers are going to try to get full code execution in the first place. This means that they will try to actually be able to run the machine code within the rendering process. So if you're on desktop, you'll be running your x86. If you're on your phone, they will be running ARM. And so the code execution, attackers are going to try to get this because there's a couple things that they can get from it, like they can now call system functions and interact with the system in some ways. They can try to maybe patch existing code if they can remap the existing code as read-write. But the question is, would you be able to actually really interact with the system from code exec? And the reason I ask this is because we come into this thing called the sandbox. So I'm sure you've all probably heard of sandboxes before. The basic idea is that we want to prevent some process from accessing some other parts of the system. So in this case, our renderer process, we want it to be protected from the rest of the system so that even if it's compromised, an attacker won't be able to reach out and touch your files or install a rootkit or something like that. And so this is obviously a security boundary that is created by the browser vendors and the operating system. And often, you'll want to try to escape the sandbox, as it's called. But as I mentioned earlier, that's not easy to do. I have to find a bug in the implementation, or I have to find a bug in another service or something like that. And that can take a lot of time to find a bug. So then you're thinking, well, okay, if we're not going to escape the sandbox, but isn't the sandbox designed to prevent us from actually doing anything interesting? And that's true. But we'll see if that's actually the case, that there's nothing interesting that we can do from within the sandbox. So that's sort of one of the things we're going to be looking at in the talk. And the way we're going to do this is by turning the browser on itself. So we're going to take browser features and use them in our new context to compromise user data in the browser and perform generally bad things. So first, as a simple example, we're going to look at something very basic to the web, which is making requests. So imagine you have a website, it's some like webmail. It might have some JavaScript that runs on it like this, where it will retrieve all your mail.json from this website. And then it will try to display that to the screen or something like that. Then it will make an HTTP request through this JavaScript to perform that action, and it will take the data and come back to your JavaScript. So my idea is, well, what if we do that ourselves, right? Maybe I want to read your corp mail, right? So let's try and access your data with a request. And so we're going to try to do the same thing, but instead of it being on this webmail.sumcorp.com, we'll try to do it from a site called attacker.com. And if we try to do the same code here, we'll actually run into an issue. We'll get a big red thing that pops up on in our debug console that says that our request has been blocked. If you look closely, it says that we're trying to fetch, in this case, Gmail from the origin attacker.com. And then there's a bunch of other information about why it's being blocked. But somehow the browser has managed to figure out we were doing something that we shouldn't have and stop us. And so the thing that actually blocked us in this example was what's called the same origin policy. So the idea of the same origin policy is every origin should only be able to access itself. An origin is basically a website, so Google is one origin, attacker.com is another. So they should never be able to interact with each other, because then if I'm a malicious website, I could then read all your data or access requests and things like that, which I should not be able to do. But so normally SOP's fine. This is a very important part of internet security. But from my point of view, I want to know if it's interesting where it's actually implemented. Because it has to be done somewhere, and since we're in a context where we can completely control the renderer process we're in, maybe we can manipulate and bypass some of these checks. So let's take a look at some case studies here of where these same origin policies are checked. I'm going to look at both Safari and Firefox for now, and we'll talk about why not Chrome, but we'll take a look. And if you take a look, you'll see that the checks are actually going to be done in the renderer process, which is what we fully controlled. So we'll be able to manipulate them to bypass. So here's the first case study. We're looking at Safari. So Safari uses WebKit as its main system framework that it uses. And inside of there, they use a thing called security origin. So a security origin basically holds some of the information about the current website that you're visiting. And it has this function called can access. Can access will be called when it tries to determine whether or not you're allowed to access another website. So if I try to open Google and make a request to Google, it's going to ask my security origin if I'm allowed to do that. And the trivial case is if it's the same origin, then yes. Otherwise, it would default to no with some exceptions. But since this is done in the renderer, we could try to bypass this. And we could try to patch it. We could modify the code. But there's actually an easier way that we can do this. So Safari has this variable inside of the security origin called mUniversal access. mUniversal access is generally used if you wanted to turn off security in Safari or in WebKit for some reason, maybe if you're embedding it somewhere. And so mUniversal access will be checked inside of the can access function, which basically, if it's set, it will always be able to access anything. So all we have to do is write a true value into this mUniversal access field, and we should be able to access any site that we want. So this is very nice, and I'm going to try to show a demo in a second here. So if you wanted to look closer, I know something's rendering it a little weird on the out here, but these slides will hopefully be available eventually. But I'm going to show a demo now of this, so let's see. So I'm going to open up Safari here. So what I'm going to do is I have a version of Safari that is vulnerable to an older JavaScript vulnerability. So this is an older version of Safari that I have a JavaScript exploit for. I'm going to open my exploit here, and it's going to start running, and it's going to leak out some information and so on. But then what it's going to do is it's going to modify the mUniversal access, and then it will try to make a request to Google. Normally, a request to Google would fail because you should not be able to get the data. But in this case, we can actually read the data, and so we get all of the response, and we can print it out to the screen. So we successfully were able to bypass same origin policy and make a request to a site that we should not be able to from my malicious site here. So let's go back here. So that's good. I'm going to quickly talk a little bit about how we could do the similar sort of thing in Firefox. So in Firefox, there isn't the same mUniversal access that makes things really easy, but we can kind of still find functions that we could patch to get this check to be disabled. The way that I found to do this is we can use the cross-origin resource sharing features. If you've ever heard of cross-origin resource sharing, it's basically a whitelist to SOP. So a website can say if another site is allowed to access it. But normally this isn't set. And so in Firefox, there's a check called check request approved. And this will basically say, OK, you're trying to make a request. Should I approve it based on the whitelist? And so we can patch this method, because this method also is within the renderer process. So it's in the process that we can completely control. And we can patch it to always return, yes, it's fine, keep going. And so I want to mention that I worked with my friend Axel. His Twitter is @overclock. He's done a lot of research on Firefox, so you can go check him out. He has some blog posts and stuff talking about similar kind of stuff. So we've now successfully shown that we can request data from other websites by compromising the integrity of the renderer process. But let's try to get a better ability here. So what's better than just making requests to websites? Well, running JavaScript in the context of that website. And this is often something that people do when they're finding web application bugs. They find what's called cross-site scripting bugs, where they can inject JavaScript into a website. But we're going to try to find what's called universal cross-site scripting bugs. The idea is these cross-site scripting can be done on any website at all. It does not have to be, there does not actually have to be vulnerability in Google for me to be able to inject scripts into it. So this is what we're going to try to do. You give me any site you want, I will run JavaScript on it in your browser from my compromised renderer process. This allows me to compromise whatever accounts are logged into that website. I'm able to read any data. It makes things a lot easier in terms of compromising the website. So the simplest way that I found, at least for Safari, to pull this off is by injecting through iframes. Iframes basically let you store or let you embed a website into your page, and then there's limited interactiveness you can do with it. So in this case, what I might try to do is embed Google and then try to insert a script tag into the body of Google's website so that it executes and I get JavaScript running. But normally, if I try to do this, there's a big problem, which is that you should never be able to access another website through an iframe. This is a protection and part of SOP. So what we're going to do is, once again, we're going to try to bypass this protection using our current permissions of the renderer process. So when we look at these iframes and how they are checked and validated when we are trying to access them, we see that there's a function in Safari called is insecure script access. A little hard to say. And it basically says, are you allowed to access the iframe? Are you the same website as the iframe? And then you can access it. And you can see it does this by checking, once again, the security origins. So security origin can access, and if it is, it will continue loading, it will be fine. But if you remember from a few minutes ago, can access actually has the universal access check inside of it. So we've already bypassed this check. Universal access gives us this as well. So I'm going to quickly show another demo here of getting universal XSS on a website through an iframe. So in this case, I'm just going to do it on example.com. So we're going to load up. And then it's going to pop up an alert that says UXSS on example.com. At this point, I would be able to run JavaScript on whatever site and compromise any accounts. And we can actually see here the iframe behind it. But it can get a little bit tricky because some sites don't like you iframing them. So what if you wanted to iframe, let's say, google.com, because that's a pretty popular site. If you try to put Google into an iframe, it will actually yell at you. It does not like it. And it's because of this pesky thing called X-frame options, which for Google are set to same origin. So same origin is basically going to tell the page that it can only be put into an iframe on Google. You can't put Google into an iframe on your website as much as you want to put a search engine on your homepage. But we're going to try to take a look and see where these checks happen and try to see if we can modify them. So once again, this Xframe options is checked within the renderer process of Safari. So inside of Safari, we have a should interrupt load for Xframe options. And then we have a switch, which checks based on the different cases. And so one is same origin, and the other is deny. So once again, we could patch this, and we could make this function always return true, which would force the always return false, so do not interrupt, so that this would force the iframe to load. But in the case of same origin, there's actually some stuff that we can do to do it without having to patch the code. Because patching the code is not always the easiest thing to do, depending on which system you're targeting. Especially if you're trying to target something like iOS, where now you have pointer authentication. Pointer authentication basically makes it harder to get code exec in the first place. So any sort of attacks that you have to pull off from code exec are not going to be as easy to do as ones that you can do just with an arbitrary read-write. So what we can do instead is we can try to modify the actual security origin object. Because if you look back here, the actual check that is being performed is the thing that says, is same scheme host port. And this is basically going to do a string compare on the domain name and like the port. So if I just take the domain that I want, which in this case is www.google.com, and I just modify my memory where it used to say attacker.com, and I replace it with this, when it does that string compare, it will succeed, and we'll be able to load it into memory. And so we can do this without needing to patch any of the code at all, without needing to get code execution in the first place. So this suddenly becomes a much more viable attack on something like iOS or a device that has some sort of protection against code execution. So I'm going to show this now. So I showed a second ago us getting universal XSS on example.com. That's not so exciting, but now we're going to do it on Google, which should be a little more exciting. So we'll open up Safari. So we exploit the render process like before, using a single bug. We get, thank you. So we exploit it. We modify our security origin so that it thinks it's Google. We load it to an iframe, which you should never be able to do. This is the only website that can load Google into an iframe right now. And from there, we inject our JavaScript in, and we've now taken over your Google account. All from a single JavaScript bug with no sandbox escape needed. All right. So now we can see that we have a pretty bad case of compromise that can be pulled off from just one bug. But we can make it worse. Where can we go from here? From JavaScript execution, you have a bit more access to some more APIs within the browser, such as local storage, IndexedDB. You can maybe mess around with the cookies for websites. But something that I found really interesting was a thing called service workers. So service workers, if you haven't heard of them before, are a special web feature which it sort of acts as this server that stands in the middle of your web application and the real network server. Usually it's used for something like cache. So the service worker is running in your browser. You request the page. It has a cached version. You don't even have to go talk to the network. This helps enable things like offline websites and other functionality that you don't actually need to go online for. But these are interesting to an attacker because it's literally man in the middle as a feature. If you can install a service worker on a website, you're now able to completely intercept all web data that is going to and from that website. And not only that, but service workers are persistent. They will continue to last until they've been replaced, depending on the browser. So this could be something that maybe you install it on a site that the user's not even logged into yet. And then one day they log in, and you capture their password in the request. So I want to see, can we install a service worker from our universal XSS? I knew that XSS was a thing that the designers of service workers wanted to try to protect against. Because if you have XSS, they didn't want it to be game over when you had XSS if you could install a service worker. So there's a couple restrictions and requirements that are put onto service workers to try to make it a little safer. So here's the four that matter most. First, the origin has to be HTTPS. So you have to be on a TLS website. This is so an attacker couldn't man in the middle of your network traffic, force install a service worker, and then take it over once it's back on SSL. But this is not a problem for us. Most of the sites we're probably targeting already are HTTPS, so it's probably not an issue. The second requirement's a little bit worse, though. Basically, it says that the script file that we're loading has to be on the same origin. So we have to find, if I want to load serviceworker.javascript, it has to be actually on the website that I want to install it on. Once again, this is to try to make it harder for someone to install a service worker on someone else's site. But depending on the site, this still might be possible. A lot of sites let you upload user data or reflects user data in some way. So we'll see that there are ways to get around this without even having to manipulate anything. But then there's two more which can be a little bit of a showstopper from XSS. One is that script file must be application JSON or JavaScript. This makes the previous case a lot harder because it's much less likely that a website will serve your file as a JavaScript file. It's usually going to be something like plain text or something like that. And then the worst one is that the service worker can only control the path that it was from. So if you're installing it from, let's say, staticworker.js, that service worker is only allowed to man in the middle the static directory. It won't be able to man in the middle the main site. That's not always terrible if they load JavaScript from that resource, but it's not as powerful as it could be. So I want to try to get around some of these. I might not be able to get around all of them, but if we can at least get rid of some of them, we may have something that can still be workable. So once again, looking at Safari, because most of my research is in Safari, I want to take a look at where these checks are done. So the first check that we cared about was that the script must be on the same origin. And this is done in this function called run registered job when the initial service worker is registered. Now, this is not actually in the rendering engine, unfortunately. This function is outside of it because the rendering engine tells the main browser to begin registering the service worker, and the first check is done here. So unfortunately, from a compromised renderer, we can't actually bypass this check directly. But there may still be ways to do it. Just within the time that I had to research this, I didn't find a direct way to bypass this check. You may be able to spoof things in IPC to get past this, but I didn't want to do that because that's a lot of extra effort in terms of the actual exploit you'd have to do. Then the next check is the file type, and then also the scope that the service worker will be installed on. So this is done in a function called validate service worker response. And this is actually done inside the rendering engine. So this is good. We can manipulate this and modify it to our advantage. This is usually done because the IPC will send back the service worker script, and then the rendering engine is supposed to run it. So before it runs it, it's validating these couple last things. But we can patch this function from code execution and force it to return that everything is valid and that there's no error. And this will allow us to first load a JavaScript file that is any MIME type. So it could be a plain text file from some sort of raw endpoint. It could be JSON. It doesn't matter. And then it allows us to install it at whatever scope we want, which means I can now, even if it's like 1 million directories deep, I can still force it to man in the middle the entire domain. So the way that you'd sort of go about this, if you were trying to exploit a user that had an outdated browser or something like that, we'd want to first find a website that we wanted to target and find a way to host the file or reflect a script on it. So this would probably be the hardest part, depending on what you're wanting to look at. Some sites you might not be able to find anything. Then, using our code execution in rendering engine, which you would get through the initial exploit, you want to patch that validate service worker response function so it does not error when we try to load the very invalid script. Then, once we've set that up, we get universal XSS on the target website using the methods we mentioned before. Finally, we tell the browser to install the service worker at the script that we previously loaded. At this point, the browser will validate everything. It will call back into the rendering engine, into our patched function, and we will be able to successfully install the service worker. So I'm going to show a demo of doing this now. So I'm going to get Safari back here. First, let's load this here. So my target's actually going to be SourceForge here because I was able to fit all the constraints. So here's the normal SourceForge. Nothing's happened to it yet. But now I'm going to go to my exploit. So you can imagine someone sends you a sketchy link, or you click something on Reddit or something, and you end up on this page. It takes only a second, and it says hack complete. A real hack won't tell you that the hack is complete, but this one does. And so this is doing all the steps that I had mentioned in the previous slide. So now if I go back to SourceForge, we'll see that it says it's been pwned by us. So this means I've been able to intercept the network requests on SourceForge, and I'm able to inject any scripts I want into it at all. Now, I mentioned that service workers are persistent. So to prove this, I'm actually going to quit Safari. And we'll open it back up again. So normally at this point, if you quit Safari, any sort of process that you had that was compromised would be gone. So the exploit would be gone. But if I come back to SourceForge, here, let me give it a second to load. It still is compromised by our process. And this will actually continue to persist because it will try to replace the service worker and update it, but the normal process will always fail, and so the service worker will remain. For one last fun thing here, let's just for fun try downloading something from SourceForge. So I'm going to download this something here. In the Tor browser, we get the DMG file. I'll open this up. And give it a second. And we can see this perfectly normal, not totally hijacked download that came from this website. So you could imagine in a real attack, potentially backdooring binaries, backdooring source code, something like that, silently from a service worker, and you would not even be aware of it. All right. So this is probably showing you, it's probably a little bit scary that you could do this from a single JavaScript bug without needing to touch the sandbox at all. But there's a few other fun things that we can show. In Firefox, for example, the sandbox does not actually protect processes from injecting DLLs into other ones, or rather just injecting code. So you can inject a tab, or you can inject code into other tabs in the browser from a single one. And then those tabs could then inject into more and more. And you could completely hijack all of the Firefox tabs until Firefox is closed. And if you want to look more into this, this was also worked on with my friend Axel. And so you can go check out his project here, where it goes into a bit more detail about doing the injection between processes. All right. So this kind of comes up to the idea of, all right, so a single bug is all it might take to compromise user data in the browser. And you think, okay, well, you still need a bug, right? It's not like this is like a thing you can just do. You still have to find a bug, right? You pore over the source code for hours and hours. Well, that's not always true, because there's been a history of browsers upstreaming bugs to their source repos that don't actually land in the main stable branch of the browser for, let's say, even a month. And if an attacker is just looking at the git commits, they may see a bug that is fixed, that may be easy to exploit, and then very quickly, within hours, write an exploit for it that has all these capabilities. Meanwhile, all the users do not have this patch, and they are vulnerable to this bug, and all their data may now be compromised. So vendors need to start working on this issue of patch gapping, where attackers can take upstream patches and write exploits for them. And this is actually starting to happen. For example, Google has just changed their time that they go from committing a security fix to getting it in stable down to 15 days instead of 33. So that decreases the time that a exploit taken from a patch will be effective against users, which is very good. But I think vendors still need to work a bit towards this, especially with the kind of abilities that I'm demonstrating here. So what else can vendors do to try to prevent this? Well, one thing they can do is try to remove some of these checks from the renderer. The renderer should not have the ability to decide some of this stuff when it's compromised. And you can also force origins into different processes, so I can't compromise the data of Google by reading its memory. And Chrome has actually started to do this with a thing called site isolation. So the idea of site isolation is that different origins must be in different processes. If I iframe google.com, well, it's not actually going to be in my compromised render process. It's going to be in the separate Google process. And then the only way that I can talk to it is through the IPC system, which is a lot more restrictive about what you can do. And unless you compromise it as well, you're very unlikely to be able to do something like bypass SOP or inject code into another domain. So this solves a lot of the issues. But there's still a couple limitations to site isolation and the general idea. So at least for Chrome site isolation, one thing is that subdomains are going to be in the same process. The idea with this is because they wanted to reduce the amount of memory usage, since many processes increases memory. So maybe if you can find a way to inject your exploit into some subdomain, you could then use that to take over the main domain and get full access. So imagine some subdomain of Google allows you to run JavaScript or put an HTML file, then you get redirected to that, and once again, now you can compromise the main website. And then also, there are certain requests that always have to be cross-origin. There's no way to block them necessarily, just straight out. And this is things like script and images and CSS styles, which historically, due to bad legacy code on old websites, people linking scripts from other CDNs, people from loading images from other people's websites, they have to retain this capability. And so what a compromised render process might be able to do is say, hey, I'm totally an image tag. Give me this data. It's for an image. And then the server would send it to the IPC, and the IPC would say, hey, well, you want it for an image? Here you go. So this would be a way to get around the fact that we can't legitimately normally make requests for other websites. So, of course, Google had to think of this as well, and so they started implementing a protection against those attacks. The idea is a thing called cross-origin read blocking, where they try to determine whether or not a request looks legitimate. Does it look like you're actually getting an image back, or are you getting some other data? Does it look like you're actually getting JavaScript? And if it's not the case, if it does not look legitimate, then we will block it because it's probably not going to be used for a legitimate purpose. And you can actually see this. So for example, if I want to make a script, and I want to make the script load google.com, which is what you could have done to try to read Google with site isolation, we'll see we get an error here that says that it was blocked by the cross-origin read blocking. And this is relatively recent, and so if you may have noticed that error occasionally. Now, I want to show one last kind of fun thing with this, which was a semi-bypass of the cross-origin read blocking. So for WCTF, Tesoro made a challenge. So he works at Google. He made a challenge to try to bypass the cross-origin read blocking. So the entire setup of the challenge was, here's a file, you have to read it. It has the flag. If we were doing it like we did earlier in the presentation, I could have just made a request, bypassed same origin policy, and gotten the file. But with site isolation, I can't just request the file directly. So I wanted to start looking into the ways that cross-origin read blocking could not apply, situations where they will just let the request through. And one of them that I found was that for multi-part requests and responses, the cross-origin read blocking would actually completely skip it because it's too complicated for them to try to sniff the data and parse out what's in there. So if a server has the ability to respond with multi-part range, then you would actually be able to bypass the sniffing and be able to read it by pretending to be a script file trying to load the data. So they say, well, it's recommended that you don't support that then on sensitive pages because it would potentially allow you to bypass this check and exfiltrate that sensitive information. Now, I've also been told that Google has tried to mitigate this further. I'm not totally sure how, but this is something that is still being worked on somewhat. All right. So not a lot of time left, but I wanted to say my main takeaways here is that the sandbox doesn't always fully protect you if your data is in that sandbox. If your data is in the browser, it may still be accessible to attackers who don't have sandbox escapes. Patch gapping can be very dangerous because a single end day could compromise all your user data in Safari or Firefox. vendors need to work on removing these control from the rendering engine like Google is doing. But even with Google, site isolation is not 100% perfect, but it's still the best thing we have. So this is where things should be headed. So that's pretty much all I have. Thank you for hanging out and listening to my talk. Hopefully it was interesting, insightful, maybe a little scary. All right. Thank you.